My name is Abigail Mortensen, and I will be presenting facilitating the bootstrapping of a new ISA. So those that worked on this project were myself, Scott Pomerville, David Whalley, Onder, and Gang-Ryung. So the implementation of a new ISA poses some non-trivial challenges, and that's due to the heavy modification of system software and the simulators. Approaches to these challenges are relevant in the area of embedded systems, and this is due to the variety of embedded ISAs, which themselves often require bootstrapping. So I'll present some of our semi-automated approaches and tools which we use to address these challenges and to facilitate the bootstrapping of our scale ISAs. So we run into a chicken and egg problem for bootstrapping a new ISA, and this is due to the testing of the simulators requiring a functioning compiler, and the testing of a compiler requires functioning simulators. And aside from this, we have some other challenges, which includes a simulator error can propagate many cycles before an observable failure. There are many code-improving transformations applied by a compiler that can possibly have many problems, and additionally, we have long simulation times with cycle-accurate simulators. Some of our techniques to facilitate the bootstrapping of our new ISAs can be generalized as the construction of a simulator without a compiler, automatic isolation of simulation errors, and automatic isolation of compilation errors. So to introduce the scale ISAs, these are some ISAs that we work on under the NSF Scale project. So the scale instruction sets were designed to communicate compiler computed information to the microarchitecture through instruction annotations. The scale instruction sets are related but distinct. The first one, our scale-based ISA, is similar to MIPS but with differing instruction formats and encodings. And the scale VLIW ISA uses scale-based instructions but schedules them into VLIW packs. So to introduce some of our simulation infrastructure, these simulators are realized by writing specifications in the architecture description language, which we call ADL, which also automatically produces an assembler and linker. Simulators made with ADL can be functional or cycle accurate. ADL-produced assemblers and linkers create a statically linked executable invoked by a simulator. So our scale-based ISA, we use this with the scale functional simulator and the scale pipeline simulator, while with our scale VLIW ISA, we use this with the scale VLIW simulator. For the compilation side of it, we've developed an assembly optimizer, which we call ASOPT, to translate base instructions to target instructions and perform low-level transformations. So in this diagram, this is showing both the input and the output for ASOPT. So we start with our source file. We provide this to GCC, which gives us 3 files of interest: MIPS object file, the MIPS GKD file, and the MIPS assembly file. So together, the MIPS object file and GKD file go together to produce something that we create with an executable there called gen.inf, which is our INF file. And then the third file coming from GCC on the bottom, our MIPS assembly file, will be given directly to ASOPT. And together, providing ASOPT with the MIPS assembly file and the INF file, we're able to produce the scale-based assembly file, scale VLIW assembly file, and some future assembly file. So, constructing a simulator without a compiler. To verify the implementation of our initial target ISA simulator and therefore solve our chicken and egg problem, we used a verified compiler for a different ISA. We call this our base ISA. An assembler which accepts base ISA and target ISA instructions, which we call our bilingual assembler, and a verified functional simulator for that base ISA. We add macros to the target assembler that accepts base assembly instructions and emits target assembly instructions. The diagram on the bottom is basically just a physical representation of what I just said. So we start with our source program. Again, we give it to GCC, which produces our base assembly program. And then this can be provided to that bilingual assembler composed of a macro translator and a target assembler. Here we have our simulator verification design. So this is, on the left, we have our verified functional simulator. On the right, our target simulator. How this works is the verified functional simulator will be ran alongside the target simulator. And for the verified functional simulator, upon instruction retirement, we'll go ahead and send that out. We'll send the associated information for that retired instruction into a pipe, And for the target simulator, upon instruction retirement, we'll go ahead and compare that with the values at the head of the pipe. If these things differ, we know something to be off a little bit earlier on, and if they are the same as expected, or let's say as we should expect them for correct simulation, we'll go ahead and continue on. So we verified the initial scale functional simulator by using a verified MIPS functional simulator, in which verified MIPS in this diagram is going to be the verified functional simulator and scale as our target. This simulator verification design layout requires very little overhead and will effectively never find the functional simulator to be a bottleneck. The verification of our scale pipeline simulator utilized the verified scale functional simulator. So despite differences in these architectures, control flow could and was used as the chief simulation variable to compare the execution of deterministic programs between these two simulators. Other points of potential divergence used to validate the target simulator include the value of destination register of an instruction and verifying values stored and retrieved by memory operations. So as a reminder, our scale VLIW organizes scale-based instructions into VLIW packs that can be simultaneously executed. However, the scale functional simulator can execute scale VLIW code by ensuring the anti-dependencies between instructions in a pack remain ordered. So we use the scale functional simulator as the verified simulator when isolating errors with the scale VLIW simulator. So now let's talk about isolating some errors with the assembly optimizer. Before we do this, I'm just going to go ahead and describe a couple of terms that we'll be using just to make it very clear what exactly we mean when we say these terms. A code-improving transformation is a sequence of changes which do not change the semantic behavior of the code and does not have to be applied for correct simulation. On the other hand, a required simulation is needed for correct simulation. An optimization phase consists of the application of 0 or more code-improving transformations of the same type. So after completion of the scale functional simulator, testing of the assembly optimizer began by simulating ASOP-produced code in which ASOP applied no transformations. Note that at this point, any MIPS instruction not supported by scale is still going to be accepted by our bilingual assembler that I showed in the earlier slide. So each optimization phase is tested individually, if that's possible, before testing it with other verified optimization phases. The correctness of one optimization phase is always going to be tested before moving on to the testing of a new optimization phase. Now I'll introduce a tool called ASOP-ISO, which is our assembly optimizer error isolator, and this is one of the main tools that we use while testing the assembly optimizer. So ASOP-ISO automates the process of isolating the first erroneous transformation applied by ASOP, which causes incorrect output during simulation. Something that it uses is called an isolation flag. So an isolation flag is an ASOP command line flag which enables a specific optimization phase to be applied where its application is thought to be the cause of a simulation error. So ASOP-ISO finds the first erroneous transformation by performing a binary search on all applied transformations of the isolation flag type or of any type throughout the program. So here's a diagram of how ASOP-ISO works. And for the sake of time, I'll just go over generally. We can categorize the execution of ASOP-ISO in 3 main steps, which are going to be represented by A, B, and C on the right of this diagram. The first one is to collect trans count data. So what this is doing essentially is taking the transformations that we want to isolate on, so these are the transformations being performed by that isolation flag, and assigning a set of numbers, which we call the trans count, which is the transformation count, in order to identify it at a later point if necessary. So we take this information and we store it to a file, and that is step A. Step B is to make the optimized assembly files. So here we're taking all the files that we think could contain a possible simulation error, this will typically be all of the files within the program, and we'll apply a set of transformations, or I should say a range of transformations up to a certain point within this group of files. The point at which we stop applying transformations is going to be that midpoint for the binary search range. And then in step C, we're going to assemble, link, and simulate the files that were brought together in the prior step B. So based on the results of that simulation, we'll adjust the binary search range accordingly, and then go back to step B, and then we will just continue to loop through B and C until the first erroneous transformation is found. So after isolation completion, ASOPT-ISO outputs 3 files: an assembly file with the first erroneous transformation applied, an assembly file without the first erroneous transformation applied, and a simulation result data file that includes the transformation number for the first transformation in the file that causes the problem. So as I mentioned before, we have these transformation counts, which are assigning a set of numbers to the transformations applied in order to identify them, and then these come in handy at the end when we have our results. We print out the associated numbers that anyone could want to use for debugging, replicating the problem, things like this. So the first 2 assembly files, or the 2 assembly files that are being output here, can be compared to directly spot that first erroneous transformation. The simulation result data can be used with the debugger to enable a conditional breakpoint in ASOPT just before that erroneous transformation is about to be applied. Here are some of the optimization phases that we apply in ASOPT. The thing that we really care about here is that the loop unrolling optimization phase has the acronym of LU. There are 2 ways we can go ahead and calculate the number of simulations required for ASOPT error isolation. The first is going to be the simulations required to isolate on all transformations of any type. And this is going to be the ceiling of log base 2 of n plus 1, where n is the total number of transformations performed in a program, and plus 1 is because of a simulation check before binary search. Now the second way is the simulations required to isolate with an isolation flag. This is the ceiling of log base 2 of k plus 2, where k is the number of isolation flag transformations within the program, and plus 2 is because of a simulation check before binary search and diff minimization. So diff minimization is a feature of ASOPT-ISO that I haven't referenced prior, but it's something that is used to increase the precision of the isolator results. So here's an application of those 2 formulas, as well as some information that was provided to those formulas. So the second and third column from the right, both under the category of number of trans, show the number of transformations being performed in the respective program. And note that this does not include library code, this is just for the program itself. So we have the number of trans for all code improving transformations. For example, for bzip2, this is going to be 16,723, compared to the number of transformations for a specific optimization phase, which is represented by LU here, standing for loop unrolling. So comparatively, this is only 39. And as a note, if this were a regular compiler, these numbers would likely be larger. So then for the following 3 columns, we have the number of simulations for a variety of scenarios. So the number of simulations for something like a sequential search on all transformations is going to be roughly half of that original number that we see. And then we have the number of simulations to find that first erroneous transformation with a binary search on all transformations. This is a more practical number of simulations, but we can see in the next column over that it is still even decreased by performing a binary search instead on all loop unrolling transformations. Most times what we're doing is using that isolation flag because testing things one at a time, this allows us to have a very good idea of where the issue is coming from almost all of the time. So with the approaches described, we were able to test a new ISA before any compilation support is provided. We were able to isolate the first instruction in the simulation that produces an unexpected result, and we were able to isolate the first code improving transformation that causes incorrect simulation results.
Thank you. We have time for questions. Any questions? Well, let me go ahead. So
Oh, there was one question?
there was one.
All right. Can you talk about the extensionability or limitation? Can you support any new ISA? Can it be something very crazy?
Gotcha. So the answer to that would be yes and no. Hold on one moment. I'm going to go ahead and make this full screen again. So obviously what's being described here is very general. We left out a lot of implementation details. And so what we're proposing is limited by one certain thing, which actually I forgot to point out. So here, when we're talking about creating a simulator without a compiler with the bilingual assembler, there is a limitation that between the base ISA and the target ISA, given an instruction, there would be an equivalent, immediate translation to the other ISA. So the two would have to be similar in that sense. If one was so completely different than the other, this approach would not specifically work. But as far as the general isolation methods, the specific tools that we are using right now were made for our team, specifically for our purposes, for exactly what we needed. But that being said, for this presentation, the things that I'm talking about are meant to be more general, for use for general things. So with some tweaking, these things should be fairly applicable.
Then let me ask mine. So you said you basically identified the first erroneous translation by applying binary search.
Yes.
That still will require some tedious iterations. Would it be
Yes.
possible to find more than one?
So at the moment it finds the first. So the actual executable that's being used only finds one. But that being said, I'll show you something. What you could do, oh, this is not the right slide. Here we go. So what you could do is specify, I'd like to search within this range, and we actually do that now. This is the configuration for the isolator. We have binary search start range and binary search end range. So if you know, okay, well, the erroneous transformation is likely to be between this transformation and this transformation, you can go ahead and search there. What you could do is you find that first transformation, and you say, all right, well, I want to check everything else too. Because possibly, yes, there could be things past that point. And you can run it the first time, find that first one, and then run a second execution of the isolator and set it to be the range of everything after. Now, this is something really manual. So as far as something automated, I'm not sure. But there would be a way to do that manually, or you could also do it in parallel as well.
So tell us what's the benefit of finding more than one?
Well, the whole purpose would be that I mean, like when you compile and you get all the compilation errors at once, that's kind of nice.
The syntax error, right? This is the runtime
True, sure.
execution isolation.
But I mean, if you have at the beginning, if you have many simulation errors, I suppose it would be useful. And I mean, you could at the first difference, you could then somehow you would have to synchronize the values and continue either with the good values or the wrong values, and then find the next one.
Yes.
And the next one and the next one. So
It might be, more practical as well. That is very manual, but it could also be practical too to make a wrapper for this, some wrapper program, and then just have it execute sections as well. If you want to check out various sections, you could separate it by program if you want, because as this is set up currently, it gives you transformation ranges for each function. So you could write a program to read in that file, something like this, on top of it.
When we fix one transformation, we find one transformation that's an error, we fix the problem in the compiler, the semi-optimizer. We hope that fixes other instances of
True.
error as well.
Okay, Okay, do we have any other questions? If not, then let's thank our speaker one more time.
Thank you.
And